Okay, good morning. Today, we are working on the exams. Aaron is a good way through it, so you'll have your grades probably in a few days. And I'm hoping everyone did well on the exam. Again, if you have any issues, questions, concerns, remember to sign up to talk. I'm happy to chat with almost anyone. Let's talk. Of concern today, and this might seem out of place, but we're going to talk about the threat of a hurricane. Here we are in early February. This is not the time of the year, as you well know, for hurricanes to happen here in the Northern Hemisphere. And we are entering a period where hurricanes can be happening in the Southern Hemisphere because the ITCZ, that line of precipitation and convergence, which moves north in our summertime, has moved south now for our winter, summer in the Southern Hemisphere. And conditions are right in the Southern Hemisphere for tropical storm formation. So, and again, just to remind you that the MRITE program is, if it's not underway yet, it will be soon. Questions for that should be addressed to your MRITE fellow, because neither Aaron nor I have the power to really do much there, so please contact them. Any questions about form, structure, etc. Question: which of these are involved in the formation of hurricanes? If we're going to be forecasting a hurricane, what are the conditions we would look for? Which of these helps in the formation of hurricanes? You can choose multiple. I think you hold down some magic button and you're able to vote for more than one. You're sitting in Fort Lauderdale. You're looking out over the ocean. You're trying to forecast whether a hurricane is forming or whether it's going to get stronger. Which of these are important in understanding the formation of hurricanes? Okay, well, high ocean temperatures has the most votes, and I would agree that's going to be a big feature here. The power of a hurricane is entirely from the latent heat release inside of clouds, and so to get the excess amounts of water vapor, you're going to want to have a high ocean temperature. In fact, so high that it needs to be at or above around 79 degrees Fahrenheit. And even more than that, it's more than just the surface temperature of the ocean, but really it's through what depth is the ocean warm. Because a hurricane, when it gets moving over the ocean, is going to be churning up the ocean. And so it's going to be causing some of the water from deeper down to come up. And the deeper the temperature is warm, the greater potential then for water vapor to evaporate into the ocean. High air temperatures are probably important only because they're related to the high ocean temperature. But the ocean temperature is really the dominant thing. You need the rotation of the Earth. Without that, you're going to get some dandy thunderstorms, but you're not going to get the formation of surface tropical storms and hurricanes. You need that for the rotation. Solar storms, really? What? They may play a role in future hurricanes, but they aren't necessarily the driving force here behind formation of a hurricane. So, this recipe that I showed you last time, we have to have large quantities of water vapor. And to get that, you have to have the warm ocean surface. You have to have the convergence of the surface. Somehow the air is going to converge on some area. One way to do that is have the ITCZ come into your neighborhood. Bring with it the convergence of winds from the north and south, and you've got convergence. But there are other ways to do that I'll speak about in a moment here. Coriolis force, you have to be at least 5 degrees away from the equator. And the wind shear. You cannot have too much wind shear. That is the change of wind direction and wind speed with altitude, because otherwise these clouds can't organize. And we left off last time talking about the formation of the Africa easterly jet. Because it's hotter in the Sahara to the north and a bit cooler here in the savanna towards the equator, it causes a wind to flow from the deserts to the south here. It gets pulled to its right by the Coriolis force, and you wind up producing a wind from east to west across Africa. And that wind picks up dust and carries it out over the ocean. But embedded in that wind are undulations. It's not just a straight wind, that when the wind gets blowing, that much like water flowing, is bound to be some waves in it. The air as it's flowing off of Africa then can produce waviness. That is, the blue line represents streamlines, we call it, where the air is flowing to the south and east here, then flows towards the north and west, and then flows towards the south and west, north and west. And these undulations in the flow of the wind as they leave the African subcontinent. And these undulations are important because they produce additional convergence over the ocean. And this place coming off of Africa, this illustrates here one of these waves. And I can think of these waves, again, as like the streamlines. This air is flowing along that blue line. The air down here is flowing on a more curved route. And just like if in a river, the river suddenly gets shallower, then the water converges into that narrow path and then diverges as it comes out of that narrow path. Likewise, these waves out over the Atlantic produce a convergence and a divergence. So we have on the right side here, the air is flowing together here. Here it's kind of flowing in a straight line. Here it's pushing into the center. So you wind up with a zone here on the east side of this wave. And this wave is called an easterly wave. Convergence happening on the east side of it. On the other side, the air is moving apart. And so on this side, you have an area of divergence. D-I-V for divergence. Convergence over here. And then the spot on the east side of this wave where the air is converging, it has to go somewhere. It's kind of getting squeezed into that narrow passage. And so this extra convergence causes clouds to form. They are pushed upwards. because they can't flow through the wave fast enough. So some of the air bottles up and gets pushed upward. And that convergence enhances cloud formation. So this zone of cloudiness then associated with these easterly waves produces bunches of thunderstorms. And then here's Africa on the right. The ITCZ is somewhere here in this sort of brown line. And this jet coming off of Africa produces a wave, and that wave does nothing more than produce an area of thunderstorms. And many of these waves produce thunderstorms and nothing happens. You get a bunch of thunderstorms, they last for a few days and then dissipate. But sometimes these thunderstorms will begin to organize. The thunderstorms are close enough together, each of them is sort of like a chimney carrying warm air higher into the atmosphere. And you get a number of these working together, and together they start removing air from near the surface, carrying it up to the top of the atmosphere and spreading out at the top. They are creating, through that process, a low pressure in the center of the thunderstorms. They are creating their own weather. Thunderstorms can do this. As they create their own system, then all these thunderstorms removing air from the surface, basically lowering the amount of air in that column, you wind up producing a low pressure in the center of this thing, and now, given a low pressure, the air can start to flow into it, and the Coriolis force can kick in, and we begin to get some rotation around this growing low pressure because of the Coriolis force. Okay, now these clouds are working together in, consortium. They are creating a low pressure by themselves, which causes the air to flow into the low, increases the wind speed, and the wind speed is flowing over this warm water and causing waves, and the waves have more water. That is the spray from the waves is flying up into the atmosphere, evaporating, and you're getting more water vapor to feed the clouds. So it's sort of self-serving that these organizational clouds do such a program that they wind up producing high winds at the surface, which creates more water vapor to feed the clouds. Diabolical. And it can continue until it becomes a tropical storm. So this is what we might call a trigger. You've got the water vapor, you've got the warm ocean, you're far enough from the equator, you've got the Coriolis force, and you got the convergence, which is created by these enhanced by these easterly waves. And this is the process through which the seeds for storms, for tropical storms, happen. On top of that, because of the topography, you asked me last time, one of the questions asked, well, how come there aren't so many hurricanes down here in South Atlantic? Well, the topography is such that in the North Atlantic, we have, the Gulf Stream flowing north up here, and it carries warm water up towards Scandinavia. And then there's a return flow along the coast of Morocco and down towards middle of Africa. And as it's flowing south here, it has access to a lot of sunlight. It gets warmer, and you wind up then with relatively warm water here from Africa all the way across the Caribbean in the return flow of the ocean. The heating along Africa here causes the water to get warmer, and that got this path of warm water. So you've got sort of the best combination here. We've got the easterly jet, let's do it in pink, easterly jet coming off of Africa. It's producing these waves out here. That's supposed to be a wave in the atmosphere as air flows across the Atlantic, and underneath it is warm water. Voila, you've got the great recipe then for forming tropical storms. So, again, this is that convergence in the easterly wave, just a variation in wind direction. It's quite subtle, in fact. Hard to pick out, but with instruments and satellites now, we can see these waves coming off of Africa because of that easterly jet. And forming zones of convergence, that would be the formation place for tropical storms. So this amazing little animation from 2017 shows from NASA, shows the formation. Africa is here on the right, and you're going to see in this animation the flow of dust off the African continent and how various tropical storms and hurricanes then form here in this zone and grow as they come across the Atlantic. Understand that not all tropical storms and hurricanes necessarily form off the coast here of Africa. It is a good path, a good way for hurricanes to form, but we've certainly had other hurricanes which simply form here in the Caribbean. The conditions are right enough. Anytime you can get multiple thunderstorms working together, they have a feedback mechanism. That's the point here, is that you're over warm water no matter where you are, and you get a number of these thunderstorms working together. Give them some time to start lowering the pressure, then that would kick in the Coriolis force and the thing can start rotating. But the key to the whole thing is a zone of convergence. Air flowing in from different directions into one area, it has to go up. So let's watch this animation. Here's you can see the dust blowing off the coast of Africa here, coming all the way across towards, here's Florida in the Caribbean. And here's a little storm forming there in the Caribbean. You almost see the easterly, the waviness in this pattern. And we're going to watch these waves. Oh, here comes Hurricane Harvey. And finally hits its peak. It kind of gets strongest now in the Caribbean. Now it grows up and causes so much damage there in the Houston area and kind of sat there for a long time and bounced along the coastline. Here comes Hurricane Irma. You might remember Hurricane Irma. You see how it came off the African coast here, getting stronger. And here Jose is next. One by one, these storms are forming out here in the Atlantic, and they have time as they pass across the Atlantic to pick up the moisture. And if they stay over the warm water, like the Gulf Stream here, Jose, lingered for quite a long time off the coast of the United States. Here comes Hurricane Maria, famously coming up the coast of North America. And how these storms then get carried off to the east. And this one, Maria, went all the way over here almost towards Ireland. Again, more air flowing off the coast. Some other hurricanes popping up along the way. But you see the pattern here, how air is flowing from east to west across this southern part of the Atlantic. And then further north, everything's going from west to east. Flow is east to west, then west to east, depending upon a latitude. And it's almost as if there's a dividing line somewhere around here, and anything to the south of that is going to cause air to flow from the east. Let's walk through that step. You've got a zone of convergence. And so here are the steps in tropical storm formation. Step one is the clouds organize in easterly waves. Or the clouds just organize in some manner because of convergence of the surface. Easterly waves is an excellent way for that to happen. As these clouds are growing, inside the cloud there is condensation happening. Water vapor is getting converted into cloud droplets. And in that process of condensation, heat is released, 600 calories per gram of water condensed, released inside the cloud. That same energy was taken up at the surface of the ocean. It took energy to evaporate the water, but then you get it all back inside the cloud. And consequently, the insides of the clouds are a bit warmer than outside the clouds, making the cloud buoyant, making the cloud want to bubble up and rise higher. So condensation is causing the column to warm up. It's warming up this area where the clouds are. And as it warms up the layer here, it's causing then the atmosphere to get a bulge above the clouds. That 300 millibars means you're through 70% of the atmosphere. You're up where jets fly. And that top of the troposphere gets pushed up because of the extra heat being released inside these clouds. Most things that you warm up will expand, and the atmosphere expands because of the extra warming of these thunderstorms. That produces then a high pressure above the thunderstorms. You push this up, so at any given altitude, that is any elevation here, the pressure in the center here is going to be a little bit higher than it's going to be on either side. There is a gradient in the pressure field up here, and the air consequently at the top here is going to want to flow away from the high pressure. Air likes to equilibrate. If you wind up creating a high pressure by whatever means, the atmosphere is going to cause wind. So, let's review that much. The clouds have formed, they've pushed the atmosphere up, they've made it warmer, and consequently a bulge in how high the clouds are. And that produces a relative high pressure above the clouds, which is then going to produce a wind away from the tops of the clouds. That means that for taking this high pressure and moving the air away from the center of the clouds here, that you are causing a movement of molecules away from the clouds. In effect, then, you are emptying that air, and that's going to produce a lower pressure at the surface. Does that make sense? You push the air up. It can't go any higher. It can't go in the stratosphere, so it just flows out away from the clouds. And as it does that, you're removing mass from this column and causing the pressure at the surface to lower. So this is the process by which clouds organize and then produce a surface low pressure system. They produce a upper atmospheric high pressure, and the flow out of it causes a surface low pressure to form. Now this is sort of the same principle as a lava lamp. You heat up a bubble rising up, is going to spread out of the top, flow down on the outside, flow back in. You produced a high pressure at the top of the lava lamp, if you know what that is, and a relative low pressure at the bottom. It's called direct thermal circulation. once that low pressure forms at the surface, now the air is going to be at the surface, be flowing in towards the low. Again, it wants to equilibrate, and there's a low pressure sitting under these thunderstorms. The air is going to flow into it, and as it does, it'll start causing waves. The waves will cause more spray. The spray will have more evaporation, and you're adding yet more water vapor to the atmosphere. So this thing is in a feedback mechanism now where it's feeding itself. Air flowing in causes more evaporation. With more evaporation, you get more water vapor into the clouds. More water vapor in the clouds causes more condensation. More heat is being released, and the column is getting warmer because of this extra condensation, causing a even greater bump above the thunderstorms in the atmosphere. And that produces a yet higher high pressure above the thunderstorm. Air flows out of it and continues to lower the pressure at the surface. And this thing there's no stopping it now. Air flows in, you get more water vapor, more condensation, more warming, more outflow at the top of the clouds, more low pressure at the surface. This is the basic mechanism through which clouds work together to create a tropical storm. Eventually, that same process is such that this rising air is rising so fast, these clouds get so strong, the air is rising so fast, this high pressure simply can't pass the air out fast enough from the center. And so some of that extra air piling up above the thunderstorms peels down and flows back down the center of these thunderstorms. And that's the mechanism which eventually will produce the eye of the hurricane. All right. This is in fact my drawing of what those tall clouds are like in a tropical storm, the eye wall of a hurricane. Tremendously large thunderstorms extending all the way up to the top of the troposphere. And they are like chimneys because so much heat is being released inside these clouds. Very strong updrafts. Next time on Friday, I'll tell the story about one of my former GSIs for the course who wound up eventually flying for the Hurricane Center into these tropical storms. And the story he has about how his plane caught on fire as they flew into the eye of the hurricane. He survives, but what a story. I'll tell that on Friday. Anyway, we have tall clouds here, tremendously strong upward motions inside of here. The air is wanting to flow out at the top away from these clouds. Not all of it can, and some of it peels back down the center here. Sinking air warms. Rising air cools. So this column in the center here is sinking and warming, and you wind up with basically a nice warm little center of the storm here, the eye of the hurricane. With the strong flow into the center of the storm, spiraling into the center of low pressure here, picking up yet more water vapor and moisture, serving that into the clouds, causing the clouds to have strong updrafts inside them. And at the top of the troposphere up here, the trying to get rid of this excess air, much of it flows away from the clouds. Some of it peels and flows back down the center. So these are the dynamics of tropical storm formation. From that, you needed the convergence, but give it enough time, these clouds will start working together to form a system of low pressure at the surface. That would allow the Coriolis force to kick in, and then you get rotation around that low pressure, and the low pressure produces stronger winds at the surface, which in turn then add to the water vapor. The dynamics are that in a hurricane you have the eye wall, extremely large thunderstorms around the center of the hurricane. You also have bands of other thunderstorms at some distance from the center called spiral bands. And they will also be rotating around the center of the hurricane. The pressure is lowest in the center. The blue line here represents the fact that the pressure is lowest at the surface. And I think I've said it before, and I'll say it many times this semester. Wind speed is a function of one thing, and one thing only. And that's the pressure gradient. How fast is pressure changing in the horizontal? So at the ocean surface here, the pressure is, it's not changing much. And then you close to the center of the hurricane, now it's changing rapidly. If you're a skier, this is the spot where I would take my skis off and walk down the hill. The stronger gradient here is the place of highest wind speed, which happens here where the eye wall is. In the center of the hurricane, which you might think is going to be the windiest spot, it's not, because there the pressure gradient is near zero. The pressure is the same here as here. There isn't much pressure gradient here, so it's relatively calm in the center of the storm. And the purple line down at the bottom illustrates that. The wind speeds pick up, and the eye wall very strong. In the eye, not much wind at all often in this idealized hurricane. This is a picture taken by, again, my former student, flying into a hurricane. And you can see inside the hurricane that it kind of has the shape of like a teacup. It's not just straight up and down clouds, but in fact kind of bent back in all directions in this bowl of the eye wall. Down here is the eye of the hurricane, and you might have some clouds in the eye here, or you might have clear sky. So let's introduce the stages of hurricane formation. The first stage is tropical disturbance. Basically, this is a stage where you're getting convergence, and the clouds are beginning to form together. There's enough thunderstorms working together, they're beginning to organize. And they persist for a period of time. Low pressure might form at the surface, but the winds remain slight. It's just the clouds are beginning to organize. There's no rotation in the cloud field. It's just a lot of thunderstorms together. It's that convergence zone in the easterly wave. This is a spot where the National Hurricane Center would start watching that zone to see if it's going to do anything. Is it going to grow up? The second stage is a tropical depression. Now those thunderstorms have worked together and they've begun to form a low pressure at the surface. And once the low pressure forms at the surface, the air is going to want to flow into that low pressure. And so you begin to get some rotation around a central spot. It's still very disorganized, but there is something going on there. Wind speeds in a tropical depression are characterized as generally less than 39 miles an hour. Windy, but not dangerous. Given time and the right conditions, the tropical depression can evolve into a tropical cyclone. Now, it's still not fully formed. There's still, you have rotation around a central point, but maybe you've got lots of clouds in the north, but not much in the south yet. It's not circular. The cloud cover isn't consistent around the center of low. Nonetheless, at this stage, the wind speeds have increased to greater than 39 miles an hour and up to 74 miles an hour. At this point, we get nervous and give it a name. And as you probably know, in the Northern Hemisphere, the names are given now these days as alternating female-male names. Used to be just female names because it was just largely male meteorologists, but enough of that. And eventually, the storm can attain hurricane status. To be a hurricane, you have to pass the physical that the storm has sustained winds of 74 miles an hour or greater. It's called a hurricane in the North Atlantic. It's called a typhoon in the Western Pacific, and cyclone in Australia. Here's a picture that shows, there's a tropical disturbance down here by Panama. You can see there's clouds together. There's a group of clouds, but they don't look particularly organized yet. This group here is declared a tropical depression. There is, in fact, a measurable low pressure at the surface, but the clouds are still getting their act together. They're not well organized yet. There's some beginning of rotation around a central spot. A tropical storm in the upper left corner here, where there are clearly signs of some kind of rotation going on, but there's a lot of clouds on one side, not much on the other side here. It's trying. It's still got a lot of precipitation in it, but it's not yet got the high wind speeds. It's not yet well organized. And then the hurricane is very well defined here. It's got an eye. This one has an eye. They don't all have obvious eyes. This one has a very obvious eye, and clearly strong rotation around a central spot here. So in this image are sort of the four stages of tropical storm formation. Last time, a couple of you noticed that there was like one hurricane in the South Atlantic. This is its picture. And you'll notice, looking at it, a slightly different pattern than we saw in the last picture. In this picture, it looks, the rotation is clear here. You can kind of get a sense that the rotation is in a counterclockwise direction. Here, off of South America, same dynamics, exactly the same dynamics, but the rotation is in the opposite direction. It's a clockwise rotation. So, important to understand that everything we just talked about is the same in the Southern Hemisphere. It just rotates in the opposite direction for reasons we will talk about at great length. Joanne Simpson, an atmospheric scientist, designed the Saffir-Simpson scale. And this scale characterizes hurricane strength. Once it's a hurricane, it has to get 74 miles an hour to be a hurricane. But once you're a hurricane, you can have different degrees of hurricane. And I'm sure you're aware of this, but there's hurricanes Category 1 all the way up to Category 5. And they are characterized here by what is the pressure. Remember, the pressure at the surface of the Earth is somewhere around 1,012 millibars on average. So even a Category 1 hurricane has a central pressure which is dramatically less. It's like maybe 30 millibars less than normal inside a Category 1. And a Category 1 has wind speeds of 74 to 95 miles an hour. The Saffir-Simpson scale is based entirely on wind speed. And the damage expected in such a hurricane is mainly to trees, shrubbery, and unanchored mobile homes. It will still do damage, but it's limited. And then you go up in the scale, Category 2, the pressure has dropped more, and this is important because, again, the wind speed is a function of the pressure gradient. So the lower the central pressure of the hurricane, the greater the difference is likely to be from outside the hurricane, the greater the potential pressure gradient. And now wind speeds are up to 110 miles an hour. Category 3, 4, and 5, each of them has ever increasing, ever decreasing pressures in the center of the storm, causing ever increasing pressure gradient forces, causing stronger wind speeds. And a Category 5 hurricane has wind speeds in excess of 155 miles an hour. And I'm sure you're well aware that when we have Category 5 hurricanes coming ashore, it's a day of great concern. These wind speeds will blow buildings apart, cause great damage, and more importantly, the high winds are, bad, but the bigger factor here is the high winds are going to cause the water to flow beneath it. It's going to push the water ashore, and that's going to cause what we call storm surge. Fortunately, those Category 5 hurricanes are relatively few. This is from 1900 through number of hurricanes that made landfall along the coast of the United States over that time period of over 100 years. And there aren't many that were Category 5. It takes a remarkable special set of conditions to get that strong organized hurricane. Lots of these Category 1s, etc. Very few so far, Category 5. If you are living in Florida, God, why would you do that? Don't do that. I'll fail you. But if you were living in Florida, question is, they're going to be talking to you about the potential for an oncoming tropical storm or hurricane. They'll use the word watches and warnings, and it's hugely important that you know the difference. A watch means it's usually a day or two before the hurricane's expected to make landfall. At that point, we have a pretty good idea where the storm is going, but we don't know exactly where the storm is going. If they've declared a hurricane watch, it's a good time to go visit your relatives in Michigan. I mean, it's a good time to get away from the coastline because, we might be wrong, but why would you take that chance? You board up your windows if you want to protect your windows and your land. Do what you must, but best, if it's at all possible, to get away. When they declare a hurricane warning, that means the storm is imminent. You've got somewhere in the next 24 hours it's going to make landfall in your area. It's probably too late to evacuate. The roads would be jammed. You should have done that already. But a hurricane warning means that you are very high likelihood of being affected by a hurricane. So know the difference between watches and warnings. Warnings, bad luck. We are looking here at various categories of hurricanes and the kind of injury and death they cause. And in the past decade or so, Hurricane Katrina stands out as the greatest cause of death in America. Now, there have been others since. You can see them listed over here, but they are a small portion of the total deaths in the United States from hurricanes. Katrina was the beast. And it was a beast because, the wind speeds were strong. It was a Category 5 hurricane, but once it got on shore, it became a Category 3 hurricane. But it carried with it, those winds carry water. And the power of a fluid goes up as the cube of the speed. That is, if you double the speed of the wind, its power to do damage goes up by 2 times 2 times 2, or 8, a factor of 8. Speed cubed. But the power of a fluid also goes up as a direct function of the density of the fluid. Wind has a relatively low density. Water has a density like 1,000 times greater than air. So if you're moving water at the same speed as air, it's going to have 1,000 times more power to do damage, and that's where storm surge plays such a huge role. This is a picture of the storm surge happening in Hurricane Sandy, which some of you may well have lived through on the coast of New Jersey. Inside the hurricane, there is this rotation in a counterclockwise way in the northern hemisphere. Notice now that there is this flow. Here's the clouds carrying the moisture up, condensing, driving the engine that drives the hurricane. At the top of the hurricane, the air is flowing out, and is flowing out in a clockwise way at the top, flowing in a counterclockwise way at the bottom, flowing out in a clockwise way at the top. Some of it can't flow out and flows back down the middle here, causing the eye. Let's focus on the surface. At the surface, the winds are blowing in a counterclockwise way here in the northern hemisphere. And I want to take a moment here in the minutes we have left today, and we're going to stop this part and go and talk about current hurricanes, because yes, right now is clearly not hurricane season here, but it is definitely hurricane season in the southern hemisphere. And so here's a map. You can see North America in the upper right-hand corner here. Here's Australia in the center. And notice this low pressure here just off the coast of Australia. Now, if you've been blessed to go to Australia, this is basically the coral reefs area of Australia here along this section. And so let's zoom in. First, you can see that there's sort of a band of thunderstorms all through here. That's the ITCZ. You can see the air perhaps converging on that area. Oh, come on, Perry. Suddenly my computer is not happy with me. So let's go here to a map from the Bureau of Meteorology and the Australian government today. There are 3 tropical storms, a tropical depression, tropical low 1, they call it a severe tropical cyclone Freddie, and a tropical cyclone Gabriel. That was what we were just looking at, was Gabriel off the northeast coast of Australia. Now that particular storm is forecast to not hit land, and it's likely to just skim parallel to the coastline here and stay out over the ocean, so it's not posing a particular risk. But just trying to illustrate that right now is tropical storm and hurricane season. There's another one, here's that other one, Freddie. There's another low pressure here out in the middle of the Indian Ocean. And we have seen these storms, they generally move again from east to west. This one is, once it gets to a certain latitude, it starts to peel off like they do in the northern